In this session, we're going to look at the definition of a radian and how it can be applied to find the length of an arc and the area of a sector. The reason that we want to do this is because it will be useful when we come to look at some more complex aspects of trigonometry, for instance, calculus of trigonometric functions or transformations of trigonometric functions. So far, when you've been working with circles, you would have used degrees to calculate problems such as finding the area of a sector. The historical origins of why there are 360 degrees in a circle is something that you can research online. Suffice to say that it's a bit of an arbitrary number, 360, and as we get into more complex aspects of maths, we want to try and come up with a more mathematically precise way of defining our unit of angle, and that is something which the radian measure seeks to do. So, the radian measure is a particular angle. It is the angle here which results when it is subtended by an arc AB equal to the length of the radius. So remember, all subtend means is a posh mathematical word for the length of the arc which determines this angle theta here. Obviously, if I was to slide this point here and move it, it would change the angle. So this length here, A and B, determines the size of angle theta, and we say that angle theta is subtended by arc AB. So if you have an angle here which is subtended by an arc equal in length to the radius, then this angle here will be 1 radian. And we can see a representation of that here. So we have the situation in which the length here is equal to the radius. So when this angle is subtended by an arc equal in length to the radius, we have here 1 radian. We could expand that to this example here. This angle theta is subtended by a length by an arc AB equal to twice the radian. So if we've already defined what 1 radian is, and this is twice the length, then we say this angle here would be 2 radians. And in fact, we can extend that all the way around the circle, and you would find that if we have defined this as 1 radian, so here the angle subtended by an arc equal in length to the radius, then we're saying that's 1 radian. We can fit in just over 6 radians in a circle, and that perhaps should come as no surprise if you think back to the formula for the circumference of a circle, which is 2 pi times r. So 2 pi is going to give us 6 and a bit of those radians. So this little bit left over is the bit. So you can see that the radius, we could get, this is 1 radius, 2 radius, 3, all 6 and a bit if we go all the way around. And we've already defined that this angle is the angle that results from being subtended by an arc equal in length to the radius. So there are 2 pi radians in a circle. So that fact that there are 2 pi radians in a circle can be used with our existing understanding that there are 360 degrees in a circle in order to convert between the two. Let's have a look then at how we can use this for finding the length of an arc and the area of a sector. So what I want you to do first of all then, if we've just got this basic setup here, is to think about a general formula which you could use to represent the length of an arc. And once you've done that, have a think about how you could find a general formula to represent the area of a sector. To think about this, first of all, perhaps it's easier to look back to the work you may have done previously with degrees. So if we wanted to find this length here, we could recognize that the entire circumference is 2 pi r, which we've got here, and then we just want this proportion, which obviously is dependent on the angle. So we would do theta over 360, which will give us the proportion of the circle multiplied by the circumference. Remember now though, we're going to be looking at radians, and we said there are 2 pi radians in a complete circle, so this proportion is going to be theta, which you need to use radians to express. Theta divided by 2 pi times the circumference, and we can cancel that down, and it simplifies to r theta, which is a very nice, easy way of finding the arc length. R times theta is how we can find it for any value, theta in radians. For the area then, very similarly, the area of a sector. Think back to work you would have done probably for GCSE. If you wanted to find the area of this sector, we know that the area of the total circle is pi r squared. We would want this proportion, which would be theta over 360. However, 2 pi radians is what we now know is in a circle, so we'd express this angle, theta in radians, divided by 2 pi, multiplied by this, and again you can see that cancels out, leaving us half theta r squared, or theta r squared over 2 as a general formula for finding the area. So let's have a look at a straightforward example then here. Find the length of the arc which subtends a central angle of 2.6 radians in a circle of radius 7 centimeters. So have a look at the formula and try and solve this one yourself. So the arc length here, we know the formula is r theta. Arc length is just going to be therefore 7 the radius times theta in radians, which gives us 18.2 centimeters. Sector area, again using the formula theta r squared over 2, substitute the numbers in, 2.6 times 7 squared over 2 leaves us with 63.7 centimeters squared for the sector area. A couple of slightly different questions now. First one here is really concerned with rearranging. The second one a little bit harder here. So the first one, a circle has a radius 2.5 millimeters. Find the size of the central angle subtended by an arc of length 9 millimeters. This second one here a little bit trickier. See how far you can get. In this circle, arc AB equals 7.86 centimeters, and the area of sector AOB equals 23.58 centimeters squared. Find the central angle theta and the radius r. Try and have a go at those, and then I will talk you through it. So this first question here, quite straightforward. The arc length equals r theta, we know that. In this instance, we know the arc length and the radius, so we're just going to have to rearrange to find theta, which is going to give us 3.6 radians. Question 2, a little bit trickier. We know the formula for the sector area is theta r squared over 2. However, we know what the sector area is, but we don't know what either theta or r squared is. We can just therefore rearrange it to give 47.16 equals theta r squared, but that's no good because it's got 2 variables for us to solve. So we need to try and find a way of eliminating one of these variables. One way we can do it is using the arc length. We know that the arc length AB 7.86 equals r times theta. So we can rearrange that in order to give us an expression for theta. Theta equals 7.86 over r. Now what we can do is just take this expression and substitute it into here, like this. And then obviously these are going to cancel down, so we'll end up with 47.16 equals 7.86 r. So we can solve r is 6 centimeters, which we found here, but we're also asked to find the central angle, and we can go back to this formula here. Theta equals 7.86 over r to yield the angle of 1.31 radians. Another question here then. The diagram shows a circle with center O and radius 5 centimeters. Find the area of the shaded region to 3 significant figures. So this is the shaded region here. How are we going to do that? Well, I'll give you a couple of minutes to try it, and then I'll talk you through it. So the strategy for this broadly is going to be, if we can work out the area of this entire sector, which we should be able to do because we've looked at the formula for doing that, we can then subtract the area of this triangle here to yield the area of the shaded region. The area of the shaded region, the sector OCD, we can use with the formula that we've looked at already. So that's going to be theta r squared over 2, theta here times r squared over 2. That's going to give us 18.25 centimeters squared. From that, we need to subtract the area of triangle OCD. If this is 5 centimeters and it's the radius, this will also be 5 centimeters as it's a radius. We've then got side, angle, side, which we should associate with the cosine rule, which will enable us to find the missing side CD. So if we, we're not actually asked to find CD, we're asked to find the area. So, yeah, the area, we would use using the area formula for trigonometry, which is going to be half times A times B times sine C, which is going to therefore give us 12.42. So we can just subtract that, which will yield the shaded area of 5.83 centimeters squared. An exam question to finish then. The circle shown has centre O and radius 3.9 centimeters. Points A and B lie on the circle and angle AOB is 1.8 radians. Find AB and find the area of the shaded region, which will be here. First of all, then find AB. So this question is going to be using the cosine rule because we've got a radius here, so this would be side, angle, side. So we can use the cosine rule to find side AB, which is going to give us 6.11 centimeters. And similarly, find the area of the shaded region. So the strategy for this is going to be find the area of the entire circle and then find the area of this sector and subtract it. So we can find the area of the circle using pi r squared to give us that, 47.78. The area of the minor sector is going to be, we've said a theta r squared over 2, that's the same thing here, which can give us 13.68. Subtract them and you will end up with the area of 34.1 centimeters squared.